Hello, welcome back to another video. Today we're going to be talking about the quotient rule for derivatives. So if you haven't watched the product rule, I went over that in the last video. The quotient video is kind of building on the product rule. It's just when you're dealing with two functions and you're dividing them. So essentially what it is it's going to be the derivative, which remember we can just write as d over dx, and we're saying that it's equal. Essentially, or the derivative I should say, first I guess I want to make sure that it's clear. It's the derivative of two functions. So really what we're talking about is the derivative of f, so one random function over another function. So they're dividing one another. And we're saying that it's going to be equal to this right here. So it's going to be basically just g, so just the second function exactly how it is, and then it's going to be f prime. So again, f prime is the derivative, so the f prime of the function minus f. So this is, we're going to minus just the actual original f function, and then we're going to end with g prime. So g prime, or the derivative of g, and then it's all going to be over g squared. So it's going to be the normal function, just squaring it on the bottom. Okay? This is important to understand. You have to understand that this has to be in the exact way you see it here. Unlike the product rule, because we have a subtraction and division, we can't just accidentally swap which order f and g's are in. So it's actually very important that you always use g f prime minus f g prime. Okay, so let's try a few examples and let's see how we can do this in practice. So what if we just had a standard polynomial? What if we had something like, let's just say 2x minus 5, for instance. So 2x minus 5, and it's all going to be over 3x plus 4. So 3x plus 4. How would we do something like this? Well, let's follow the rule and we'll see what occurs when we do. So first, if you remember, we just want to go with g. So the bottom function would be 3x plus 4. We're just rewriting the bottom function, okay? All right, then we just do f prime. This is f prime, so let's multiply it by f prime. If you recall, the derivative of x is 1, so derivative of 2x is 2. And then the derivative of any constant is 0. So it's just going to be 2 is your derivative there. Then you're going to subtract f, so just what f is in the function, so 2x minus 5. And then you're going to multiply that by the derivative of g, so the bottom function. And kind of like before, we know the derivative of x is 1. 1 times 3 is 3. And the derivative of a constant is 0. So it's just going to end up being 3. And this is all going to be over g squared. So the original g function, we're just going to square it. And how that looks like is simply just 3x plus 4. And we're going to square the whole thing. Okay? All right, and do remember that if you're having trouble understanding where I get the derivative of x or constants, I do explain it in my intro to derivative video. Okay, so when we're trying to figure out the actual derivative, this is the answer. We just have to simplify it now. So 2 times 3x is 6x, 2 times 4 is 8. And then we're going to remember, always keep the subtraction sign when we're dealing with this until we get the answer at the end. So 3 times 2x would be, again, 3 times 2x is 6x again, so it turns into 6x. And then 5 times 3 is 15. Then we just have to put the bottom down, so this would be 3x plus 4 squared. And then we just kind of going to very briefly simplify the last bit here. So it's going to be 3x plus 8. And then again, we distribute the minus, so that's negative 6x. Minus for the 15, it turns into a positive 15. And then so if we basically, and remember that we do want to keep always the bottom rewriting. Even though it remains the same, usually the bottom isn't going to simplify. We want to make sure that it is staying the same regardless. In this case, though, we have an interesting thing going on with the function. It's going to simplify, so the 6x and the negative 6x will cancel, and 8 plus 15 is going to be actually just 23. So it's going to be equal to 23 over this original 3x plus 4 squared. And let me just make that a little bit better of a x there. So that would be 3x plus 4 squared. So the answer just ends up being 23 over 3x plus 4 squared. And this is how you would do the derivative. Not always do the x's perfectly cancel out with one another, but the actual process is the same. So I'm just going to erase this and come back for another example for us. Okay, welcome back to another example. This one we're going to be doing something at a bigger polynomial, let's just say. So x squared minus 3x plus 4 all over, let's just say, x plus 2. Okay, so to do this, we first do the same thing as prior. So we're going to be first putting our g function just as it's presented right there for you, so x plus 2. Then we're going to be taking our f prime. So the derivative of x squared ends up just being 2x, because we're bringing down the 2 and decreasing it by 1. And then, of course, 3x's is just 3, so this is a minus 3. And then, of course, 4 is just 0, so it ends up just being 2x minus 3. Then we're going to subtract the f function. The f function in this case is going to be x squared minus 3x plus 4. And then we're going to be doing the derivative of g, which if x's derivative is 1, and then 2's derivative is 0. So 1 plus 0 is basically just 1. So the derivative is just 1. And then we're just going to have this all over the x plus 2 squared. So just like before, this actually is the answer. We just want to essentially simplify it a little bit. So you can do anything you want when you're simplifying these ones. You can FOIL it, so we can do FOIL it in this case. So x by 2x would be 2x squared. And then we're going to have x by negative 3, which turns into negative 3x. Then 2 by 2x turns into 4x. And then 2 by negative 3 will give you negative 6. And then we're just going to keep this subtraction here, remember? In this case, it doesn't matter because it's just a 1 here, but it's important to get into that habit. But in this case, it just is going to be distributed off the bat since it's just a 1 here. So that's a negative x squared. A negative and a negative is a positive, so plus 3x. And then a negative from the 4 would be a minus 4. And again, we are all over the original x plus 2 squared. Okay? All right, now we're going to try something. We're just going to basically simplify it. So we have a 2x squared and a negative x squared, so that just turns into an x squared. A negative 3x, and first of all, a 4x will give us x as a term. And then x plus 3x will again give us 4x as what we want there. So it would be equal to just 4x. And then we have just this negative 6 and negative 4, which just become negative 10. And of course, this is just all over again, x plus 2 squared. So like I said, this is the answer. It's the same thing as this one. We just simplified it, all of the terms. But this is the same thing. So this is your answer to this one. I'm going to come back. We're going to try another example. All right, welcome back. We're going to be doing the derivative of differing functions. So we did it some polynomials, but I want to show you that it can apply just to many, many different functions and have the same exact process every time. So in this time, we're going to focus on ln's or logs. So we have the x squared of ln of x. So how would we do this? Well, the same thing as before. Let's start off writing our formula. So we're going to first have our g. Our g's are bottom one, so the ln of x, we're just going to write the ln of x exactly how you see it. Then we're going to write f prime, so the top one, x squared's derivative would be 2x, as we said before. And then we're going to subtract f. So f, remember, is just x squared as it already existed. And then, of course, we're going to have ln of x, so the bottom function's derivative. So ln of x's derivative, I went over this, the product rule as well, but it's just one of them you have to know. Ln of x's derivative is 1 over x. So 1 over x is the derivative there, and we're going to put this like this. All right, so now we just have to basically finish off the bottom. So we know that g squared, that would be ln of x squared. Okay, so now let's go ahead and write it out again. So ln of x and 2x, we just kind of put that as a product of one another. And then x squared of x, though, we can put this on the side. We can say this is x squared over x if we were to multiply them across. Well, 2 minus 1 is 1, so this is actually just x. So this whole thing is actually just x. And then this is all going to be over the ln of x squared. So this is your answer, and as you can see, you really have a very similar thing going on for the most part. Okay, welcome back. So let's just say we had something like an exponent this time. So we did ln's or logs. Now let's do exponentials to try out that avenue as well. So again, the process remains the same. So first we're just going to have the g function. So the bottom function would be e to the x. Then we're going to have the top one's derivative. So that would be 3x squared. Then we're going to subtract the f just as it is. So x cubed. And then we're going to multiply that by the derivative of the bottom. And the derivative of e is just e to the x. And of course, this is all going to be over g squared, so e to the x squared. And now we're just going to simplify it. And as you can probably notice, there's not a whole lot you can do of simplifying here. This is just going to be e to the x by 3x squared minus e to the x, x cubed, and then this is all over again, e to the x squared. And this would be your answer. You could factor out an e to the x in the top if you wanted. You don't really have to. E to the x or x, you could factor out that if you'd like. There's no need to do that right now, but this is the general idea for e to the x. Okay, so now we're going to let's try something like a trig, for example. So what if we had something like sine of x over x. Could we do something like this? Like I said, it's the same thing as before. We just have to take it in that way. And you could do this as a product as well by making a negative exponent, but let's treat this as a quotient this time. So again, we would take g, so that would be x. Then we're going to multiply by the derivative of the top. So sine's derivative is cosine. Then we're going to subtract just f, which is going to be sine of x. And then we're just going to go simply and say that it's going to be g prime's derivative. So that would be 1. And then again, we're going to put this all over g squared. So this would just be x squared. All right, and then let's try to simplify this down a little bit. So this would be x cosine of x minus the sine of x over x squared. And this will be your answer. So as you can see, the process does become pretty straightforward after a while. It doesn't take too much finicking around at times. Let's also try something similar, but it might not seem like you have to use the quotient rule. So let's say if we had something like the tangent of x. So sometimes, if you might have watched my intro video, I go over the basic trig derivatives, what they are, and it's a memorization game essentially because it's important to understand what they might be, just doing it that way. But it comes from a way, and the way it comes from is this quotient rule. So if you recall, tangent derivative is just going to be secant squared of x. But let's prove that using the quotient rule. And the way we can do that, we first want to rewrite this as f of x equals to sine of x over cosine of x, because if you remember trig, this is what tangent equals to. Well, now we can use the quotient rule. So if we wanted to do this, we would say that first it's going to be just g, so cosine of x in this case, so cosine of x. Then it would be basically f prime, so sine's derivative is cosine, so it turns out to be cosine of x multiplied by cosine of x. Then we're going to subtract just f by itself, which is sine of x. And then we're going to multiply that by g prime. So cosine's derivative turns out to just be negative sine of x. And again, this is all going to be over g squared, and this is, of course, just cosine squared of x. So you can think of this as cosine x squared, but it's technically usually written as cosine squared of x. So now let's just simplify some things out. So this would be cosine of x, that's cosine squared of x. And then if we notice, this is going to be a sine of x, this is a sine of x, so sine squared of x. There's also a negative here, though, so a negative by a negative will just give you a positive, so negative and a negative. So this would be a plus sine squared of x, and this is all again over cosine squared of x. And if you recall from trig, we know that sine squared of x plus cosine squared of x equals to 1, and it doesn't matter the order. It can be cosine or sine since we're adding them. So cosine squared plus sine squared actually just equals to 1. So we can rewrite this again to basically this whole just turns out to 1. And this is cosine squared of x. And this looks like the answer, but if you recall, cosine squared of x or cosine of x, 1 over this, can be simplified to secant. Secant is equal to 1 over cosine. So really what this is equal to is secant squared of x. So as you can see, we prove that tangent's derivative is indeed secant squared of x. But this is how we get it, and you could do a similar thing for all the other ones. Cotangent, cosecant, secant, they all have a very similar process. But you can tell too that secant doesn't, it makes a lot more sense now since really it's 1 over cosine squared of x. Okay, so this is an introduction to the quotient rule. This is really how the process goes. At a later date, I will go over more complicated product and quotient where they're combined with the chain rule, which we haven't been taught yet, but the chain rule usually goes hand in hand with them. And it has a little more simplifying. But this, in terms of your fundamental quotient rule problems, this is what you're going to be dealing with. So I hope this helped. Thanks for watching.